Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Damien Bégué with us today. Hey, Damien.
Hi, thank you for inviting me.
Well, thank you for agreeing to talk about your very lovely article. Super.
Yes, very nice to be here.
Damien, where are you located at?
Right now, I'm actually in Israel, very close to Tel Aviv. I'm working at Bar-Ilan University with Professor Asaf Pe'er. So, quite hot at the time. Yep.
And it is March 21st, coming up on equinox here as we record this one. So very good. So is it spring yet in Israel?
Yes, it's well, spring, almost summer. Actually, it's very hot.
Yeah,
Yes,
a little closer to the equator. Very good.
Yes.
So I'm in Phoenix, and we're getting a weird day today. We're getting a little reblast of winter today. So it's been fairly warm, but today a cold front has rolled through, and we're going to be all chilly and rainy and everything. So yeah, winter.
Yeah, lucky you.
Very cool. And I gotta say, you have one of the most awesome background images. That looks like you have some children.
I do. I have two kids, so it's you see there is Christmas tree behind me. It's always Christmas at my apartment. So yeah, they just love it too much. They don't want a tree unmounted, so it stays. That's okay.
Every day is Christmas, and every night is New Year's Eve.
Not without the present, though, right? Without the present.
Very cool. Very cool. And Damien, what do you like to do for research?
Well, I'm involved in a lot of different topics. So I'm mostly coming from the field of GRBs, gamma ray bursts.
Okay.
So I don't know if I should say a word about this or not, but it's basically those very violent explosions that happen at the end of the life of very massive stars, or maybe you heard about them when you have merger of two neutron stars. Yeah, so that's what I do for research mostly. And since about 4 or 5 years, I started doing GRMHD, which I'm going to discuss now. Cool. And the reason is because I want to apply those things to GRBs, to the physics of jets, to the physics of accretion inside those wonderful engines.
Very nice. Very cool. And that is going to bring us to this very lovely APJ supplement article. It's open access. You can go get a copy for free, people. Go grab one. cuHARM, a new GPU-accelerated GRMHD code and its application to ADAF disks. And Damien, take us away.
Yes, thank you very much. So this is a paper that we wrote about, say 6 months ago now. It was published only like 2 months ago. So we basically do two things in that paper. The first one, we write and design a GPU-accelerated GRMHD code. So this with the aim of solving, of course, GRMHD equations.
Okay.
That's one first part of the paper. Okay. And the second part of the paper, we basically applied this code to the physics of ADAF disks. Okay. I will discuss this in a little bit. And we have two reasons for this. First, they are amazing objects; they are very interesting. And the second thing is because it's actually very well studied. So for us, it's important to actually have a code that makes sense, produces reliable results. It's a very difficult topic, and it was interesting to be able to reproduce already known results as well as to derive our own results.
Cool.
All right. So if I can give a sharp introduction, so when it comes to accretion disks, we find accretion disks nearly everywhere. So as soon as you have some systems that are accreting, you will definitely have an accretion disk. This is normal.
Yes.
We basically have say 2 states of accretion disk, right? So we have the sane and the mad. So the sane, it basically stands for standard and normal evolutions, and it's basically a disk in which the magnetic field does not play a major role. And what I want to say here, I need to be very specific because basically the magnetic field produces a viscosity that enables the accretion, right? But what I mean by does not play a major role, what I mean there is that it does not impede the accretion. It does not stop the accretion. Right. And this is contrary to what, for instance, we have in mad disks, so which is mainly arrested disks, in which the magnetic field basically becomes so intense at the center, very close to the black hole, that it limits the accretion.
Yes.
Okay, so that's what I meant by the accretion disks actually now plays a dynamically important roles. It's that it actually blocks the accretion. So what I'm going to discuss now is basically sine disk. So the only role somehow of the magnetic fields is to transport angular momentum throughout the disk. And that enables the accretion. It also produces jets, right?
Yes.
Okay. So this is basically what we want to do when it comes to the physics. Now, when it comes to the numerics, is that if we actually want to solve for the motion of plasma very close to the black hole, we basically have to solve GRMHD equations. Right, and for this is something that is very complicated stuff. So you have, of course, analytical solutions. But if you want to start doing 3D, if you want to start looking at instabilities and other things like this, then you necessarily need to have something that solves your GRMHD equation numerically.
Correct, generally. Yep. Cool.
Yes, and so, as I said, this is a very difficult topic, but it's also extremely time-consuming. Solving those equations in full 3D is difficult and time-consuming. So what we basically did, we basically started from a non-code. I guess this is a little bit further down if you're looking for it.
Fine, it's great.
Okay. So we basically started from a non-code that is called ARM from GAMI. That's published like 20 years ago now. It was the original paper is in 2003. Now the advantage of this code is that it is basically thoroughly studied and it's very well documented. So we basically started from this. Now we have improved the numerical techniques that are inside this code. We basically also made it 3D. And I think one of our largest contribution there is to actually that we accelerated the computation on GPUs. So a GPU stands for graphical process units. So this is the thing that everybody has in his computer that basically allow you to use your screen.
Yes.
And the reason why it's very good for what we want to do is because they are hardwares that are designed to always repeat the same operations in parallel. So this is what when your screen happens, right? It's always computing what color it needs to print on every single of your pixels.
Right.
Nothing more. So if we can somehow manage to reduce the problems that we have to something like this, of course, not showing colors, but something in that order, then basic GPUs become very well suited for those types of computations. So now, if I want to analyze this, maybe you can go to figure 1. That will help to understand what is going on. So basically, we're trying to solve partial differential equations that are, you can stop here, sorry, that are given by equation 1, 2, and 3. Oh, I have delay, I'm sorry.
That's okay. Yeah, we have a little bit of bandwidth lag. It's all good. So
yes, here. So we are basically attempting to solve those equations. So those are ideal GRMHD equations.
Yes.
And we basically discretize those partial differential equations on a grid. So now we can go to figure 1. And this is page 9.
Yes, figure 1. There we go. That looks good.
Exactly. So to discretize to solve those equations numerically, we basically discretize them on a grid. So here I just show a 2D grid. You can look on the left, and you actually have the same in physical space on the right. And so basically, what the code do is to always perform the same operation for every single of those grid points. So you can now very easily imagine that those are nothing more than the pixels on your screen, right? And this is why now GPUs become extremely efficient. They are designed basically to do those types of computation, and they are very fast and very good at doing it. So we basically designed a GPU code. So our equations are solved on a GPU. And I do not really like to give gain of time, but if I have to make a fair comparison, it would be about a faster 10 times faster between the GPU on my computer and the CPU on my computer. So this is the order of magnitude that we are roughly gaining by using a GPUs. What I think actually is that in the future you will see more and more such codes, not only GRMHD but also other types of code that will be designed and run on GPUs. So that's a technical solution that can be easily implemented.
Right, embarrassingly parallel. Yep.
Exactly. So So this is basically it when it comes to the GRMHD. We are using nothing more but already published numerical methods that are readily available everywhere in the literature. It has been very difficult to put all of those things together. I mean, on the paper, it's always very simple, but when it comes to actually do it, there are always some small tricks everywhere. Yes, exactly.
Yes, there is.
So, but well, we think we managed. So we have basically tested that code on a lot of test problems, and mostly actually special relativistic problems. The issue being that when it comes to GRs, there are not so many analytical problems that we can compare our numerical results to.
Right.
So I think we actually have this in the appendix later, but basically we have compared the numerical results that we get with other codes results that were published about 4 years ago now. Okay. So that was in the context of the EHT, the experience that take a picture of a black hole of M87, right? So they basically needed to understand whether the numerical code would converge towards say same solution. Okay. And so they basically wrote a paper to discuss the agreement between the different codes that the community is using. So we basically used the result from that paper to also check that we get the same result. Good. So on that end we did, and we were very happy of this. So that was somehow a good confirmation that we are not doing too many silly things. There you go. I will put it that way. Okay, so now maybe we can go to the physics of the paper. Okay. So as I mentioned in the introduction, we basically want to look at sane accretion mode. Yes. So the reason why we actually started by this is, as I said, is that it's numerically simpler. Right. So there are less tricks that are involved. So it's easier. And so what we did, we basically ran a certain number of simulations, and those are given in table 1. Table 1. Yes. Okay, here we go. Okay. So here you see we basically have 9 simulations. They have different characteristics. So what I should say first is that we start from an initial condition that is a fishbone Moncrief, which is what most of the people actually do today. And our typical resolution is something around 256 times 128 square. So that would be 256 grid cells in the radial direction. Yep. And for both angles, so phi angle and polar angle, that would be 128 square. So those simulations typically take about 3 days to run, which is affordable for us. So that's great. And we can only do that because we have GPU computing. If not, it would take way longer. 10 times longer. Exactly. So basically, we have run 9 simulations that differs from initial magnetizations for different adiabatic indices. So you see, for instance, if you compare, yes, exactly, the adiabatic index is on the 4th column. So we have a non-relativistic adiabatic index and relativistic adiabatic index. And we basically wanted to check, for instance, what is the influence on the accretion of the adiabatic index. So we can discuss that a little bit later. What we actually did that a lot of people did not try, we also started from non-steady situations. So the problem of using a fishbone Moncrief and slightly perturbing it is that, so you want to perturb it so MRI kicks in and you basically accrete your material, right? Yes. The problem of doing that is that this is unlikely that nature will produce this setup, right? You don't really start usually from an equilibrium situation and start shaking it a little bit. So we actually wanted to see what happens if you actually start from a non-equilibrium setup. So what we did, that would be our run 5 and 6. So what we basically did was to start from a torus that is not at equilibrium, and we initialize the torus with non-relativistic adiabatic index. Okay. And when we evolve, we actually change the adiabatic index. So what happens basically is the torus collapses on itself, and then this is helping to trigger accretion and MRI kicks in. So really basically what happens is that it just collapses. And then from that point of view, we don't start from a steady state, which was, we wanted to see what happens in that case. Good, very good. Okay, so if we go, for instance, to figure 2,
Figure 2.
so this is page 10.
10, figure 2. Let's do a global on this, and then we can zoom in as need be. Okay.
Yes, exactly. So this figure 2 basically shows 4 quantities that people like to measure when it comes to understanding accretion rate. So the first one on the left, which is the most important one, is basically the accretion rate. And the one on the right is the magnetic flux reading the horizon. Okay, so those two would be the two most important ones. So if we zoom in on the mass accretion rate,
yes.
the one on top left.
Yes, and let's zoom in on that accretion rate. There we go. Let's back that off a little bit. There we go.
Yes, okay, perfect. So basically, this is the mass accretion rate for all our runs. And so we basically get something that is similar to what a lot of people have obtained previously, right? So we basically have a period of transition where our torus, because it was destabilized, basically starts accreting. So this would be at very early times. You see they have this very sharp onset. Yes, yeah, exactly, right exactly there. Yep. So this is a very violent onset of the accretion.
Yes.
And then it steadily converges towards a quasi-steady state situation. Yes, which is obtained at late time. So this will be between 5,000 M to 10,000 M.
Okay.
Right. And so you see that after this, basically nothing very thrilling happened. We pretty much have a constant mass accretion rate, and that's about it. And this is what we get actually for all our simulations. The only one that do not satisfy this is actually simulation 5 and 6. Yeah. And those were the ones that were starting out of equilibrium. Yes.
Right.
And so what happens for those simulations is basically instead of reaching very fast this quasi-steady state, yes, because it's the torus collapses, and this is triggering a shock wave inside the torus that is accreting. And so accretion proceeds now in kind of a more disturbed ways than it was doing for the torus for which we start from equilibrium. Okay.
And, if these are your steady state values, it looks like these two end up with larger m dots.
Yes, they also end up with larger m dots. This is right, and so we actually think that what happens is because we start from the flow inside the disk is very unsteady because it collapses, so it triggers shock waves, and so we think that this is actually accelerating the process of accretion. Now it's a little bit the same problem that we have, when we start from this steady torus, right? Is that it's also it's also an artificial start, right? Yeah. So it's difficult to say, whether this would actually happen or not.
Understood. I'm good.
Okay, so now another thing that I would like to discuss, if I retrieve my paper, is actually the influence of the adiabatic index. Okay. On the jet structure. So if we go on page 5.
Page 5?
On page 15. Sorry, on page 15 for figure 5.
Figure 5. Okay, and pretty. There we go. Let's.
Yeah, the figures are quite heavy, and so it's a little bit laggy. I'm scared. Okay. So those figure shows is we can just focus, for instance, on the top line. So it shows the density. So this is in color coding. It's logarithmic of density. It shows the plasma beta parameter, which is gas pressure over the magnetic pressure. Yes. And then it shows sigma parameter, which would be the magnetic field intensity or magnetic pressure over density. Over rho, over the density.
Over rho. Okay, I'm with you.
And all of this is in log scale. Okay, all those quantities are shown in log scale. Yes. And those quantities now, they are time averaged and phi averaged.
Okay.
So basically what we have here is an average picture of our accretion flow. Right. And so you see that the accretion flow is basically split into 3 different parts. So at the center, at the equator in red for the density that you're showing right now, excellent, yes. This would be our disk that is being accreted right now. Then we have, in blue at the pole, this would be the jet. So this corresponds to a magnetized region. You get actually on the right and on the central and on the right pictures, you see that it's magnetically dominated. And yes, so this is the magnetic jet. And then you have a region in the center between the disk and the jet that is called corona, where basically this region is very turbulent and it carries a lot of mass outwards, so it produces wind.
Okay, and you can get that sense from this beta shot here, just the difference.
Exactly. So what we basically looked at is whether there is a dependence on the adiabatic index for the shape of this jet. So basically for this empty magnetized region at the center. Exactly. Yes, we are looking how wide that things become. Exactly. And so if we go to figure, it is here, to figure 10 on page 19.
Sure, and just so people follow along, there's lots of these for the different 9 simulations that we're running.
Yes, exactly. So we are showing them for all the simulations. We have provided comments, but I think we don't have time to cover all those things, and so it's better we focus, I think, on the key result. It is the figure just above.
Oh, 10. Sorry, thank you.
Yes, on figure 10. Yes, exactly here. So basically, what this figure shows is the position of the sigma equal 1 line. So this is basically the transition from the magnetized region to the disk.
Okay, I'm good.
Okay. Mm-hmm. All right. And we basically show the angle measured from the pole as a function of the elevation above the equator.
Height, yeah, okay. Mm-hmm.
Okay, so on the x-axis, this is the elevation. So how high you are above the equatorial plane.
Yes.
And the y-axis here is the angle. And so what you can see right away is that you actually do have a difference between the two adiabatic indices, right? Okay. So the adiabatic index with relativistic pressure is actually wider than the adiabatic index with non-relativistic pressure. Mm-hmm. And so it can easily be understood because when it comes to relativistic adiabatic index, the pressure is larger, so we are compressing the jet towards the pole.
Yes, yes.
Okay. Mm-hmm. Mm-hmm. Great. So basically, now we are basically trying to find a way whether we can try to use those informations to measure the adiabatic index inside the disk. So this is one of the things that we are looking into right now.
Cool.
But now when it comes to, for instance, accretion rate, other properties of the disk, or flux readings horizon, magnetic flux readings horizon, there is absolutely no difference, or no difference that was reported. So the only encoding information somehow is inside the width of the jet.
Yes.
For the adiabatic index, and this is somehow consistent with previous studies. So some other people actually looked into variations of accretion rate, so temporal variations. And the idea would be that temporal variations would also reflect the adiabatic index, the value of the adiabatic index. And what they actually found is that this is not the case.
Yeah.
Okay. You don't seem convinced, but that's
no, I believe you. I was scrunching on it that there would be a temporal variation, so my intuition was okay.
Put it that way. They tried it, and the answer is that they did not find anything, and basically so did we. So the only thing that we can report is basically this difference here of width.
Yeah.
All right. We basically tried a lot of other things. So, for instance, we tried to understand how our mass accretion rate would depend on our magnetization.
Yes.
So this would be shown, for instance, on figure 12.
Figure 12.
Just below.
Okay, we got 2 panels here.
Yes, so we can just focus on the left. Okay. On the left panel, yes, exactly. And so what this figure shows is basically how the mass accretion rate is changing as a function of the magnetization inside the disk that we put by hand when we initialize our numerical setup.
Very good.
And so basically what you can see is that there is no trend whatsoever that seems to appear right away. And so this is good because in principle, we want the magnetic field inside the disk to develop by itself with the effect of MRI. We don't want that the accretion rate depends on our initial setup, on our magnetic field.
Right. For a sane disk, yes. Mm-hmm.
Yes, exactly. For a sane disk, if we go to a matte disk, of course we want this to change. Yes, this is but it's another debate, right? Yep. This is another debate. I mean, on that point, actually, if you go to show the right picture, so this would be showing what is called the MAT parameter. So this is the magnetic flux trading the horizon normalized by the square root of the mass accretion rate. And so again, also as a function of this initial beta zero. And you see here again that unless we start going to very small values of beta zero, so basically very large magnetic pressure, initial magnetic pressure, then we do not really change the value of the MAT parameter. So basically what it means is that our steady state situation does not really depend on the initial setup that we have there.
Yes, that's important. Good.
Okay, so I would like to discuss two more things, maybe.
Yeah, sure.
So the first one is the figure that is right above, so I can use it to contrast just later. So in that figure shows what is called the barycentric radius of the disk. So in essence, if you were to concentrate all the mass of the disk in one point, what would be its radius? Okay. That makes sense? All right. Okay, great. And so what we are looking at here is a time evolution of this barycentric radius for 4 different simulations, which are varying initial beta zero. So initial magnetization inside the disk. Okay. So if I have to make comment on this, so what we can see is that the higher the magnetization, basically, the faster the spread. And this is just because when you start with higher magnetization, viscous spreading is faster, and so you can carry mass away faster. Okay, this is entirely something that is due to the initial setup. Okay, there is no real physics behind it. That's what I mean. Okay, we would need to look at what happens at late time. So say after 8,000 M, so you see they will all start to converge toward the same radius. Okay. So where I want to go now with this, as I told you earlier, we actually had 2 simulations that were started out of equilibrium.
Right, 5 and 6.
5 and 6, exactly. And so for those simulations, actually the setup is very different. What we get for this is very different. So if you go to figure, sorry, here I got 14. So this is 2 pages below.
Okay, let me just put this in my short-term memory bank. Gotcha. Figure 14. Oh, yes. Little different.
And here we are, exactly. So you can see that they actually are very different. So just to be clear, those are basically 2 simulations with the same initial setup, but with 2 different resolutions. So we wanted to see at what point basically our things were breaking. Now, what I think is very interesting is what happened at early times, not what happened at late times. Okay, so if you recall what happens at early times for the other one, basically the disk just spread.
Yeah.
Now, in that situation, actually, what happened is that the torus contracts, collapses on itself, and this is actually triggering accretion. So basically, the disk converges closer to the black hole. And then we have a second shock wave that is launched that is pushing against the material towards larger distances. And this is this bump that you can see here.
Yeah, okay, got it.
Okay, so basically what I want to say here is that somehow if we look at early times, and well, this is more or less obvious, but the accretion history somehow depends on our initial conditions. And we wanted to check how those things would evolve. What we find is that if we start for the same initial setup, but from equilibrium, the jet will actually disappear. Right, so basically the existence of the jet in that case or in the other case, we get that the jet just disappear. So we don't really know what the actual reason is. We as you see, we have run until then to just 10,000 M. So maybe if you run them for longer, then the jet will reappear. And this is things that we are actually doing right now.
Cool.
But basically, the presence of the jets does depend on this initial setup, which is if you want to study jet, maybe you just want to start from a setup that gives you a jet. But the link between the jet and the disk, maybe there are things to look at how accretion history regulates the presence of the jet or not.
And just to state sort of the obvious here is a fairly large dependence on the resolution, right, in the theta direction.
Yes. There is a large dependence on resolution at late times. Also, when we look at those at those diagnostics, there is not much of a difference. So this is a little bit weird that there is a difference here. But okay, in principle, it's like 10%, 15%. So
fair enough. Okay, good.
So that's it. I think I covered the most important points of the paper.
Cool. Very nice.
Maybe I can I can summarize in 2 words what we did.
Sure.
So we basically wrote a GRMHD code that is accelerated on GPU, which is great. It's working. This is even better, right? We are basically now steadily starting to use that code. So we have several students working on different aspects, be it programming or be it physics, right. And we hope to be able to publish more results soon with it.
Cool.
So thank you.
Nice. Very, very nice. Very nice. Damien, I want to thank you once again for walking us through your very lovely supplement article. Very cool.
Yes, thank you for having me.
Yeah, I mean, you touched on it a little bit there at the end, but let me go ahead and push on it a little bit, or at least ask for some more detail. And so where do you think we go with this over let's say the next couple of years? Is there additional coding work to be done to get yet another factor of 10 out of it? Are you going to be applying it to different scenarios? Is there theoretical work that can be done? Is there any observational work that could be done to help verify some of this? And just sort of where do we go over the next couple of years?
Well, right. So I can say where I go over the next couple of years. So where I go over the next couple of years, so we have a lot of coding involved. We are basically looking at radiation output from those things.
Ooh, right.
So this is a lot of work. We have ASAF pair as students working on this. Okay. We are also obviously doing physics a little bit. So we are going to publish quite soon a paper on MAD, on the MAD scenario.
Okay, cool.
And we are also looking at accretion scenario in compact binaries in XRBs. Okay. So this would be for the physics. Now, to answer your question about more coding to get another factor 10, I want to comment on this because this is something that is touching me. I think the problem is that improving the performances is always coming at the detriment of working time on other things, right? And right now, I do not feel that improving the performances would be fair in correspondence to all the physics that we can extract to those things now. So more coding to improve the speed, no. More coding to improve the physical ingredients, yes, absolutely.
Okay, understood. Very nice. Very nice. Well, very cool. Well, I look forward to seeing the additional physics that comes in and the additional applications that it's put to, of which you alluded you have several interest in at the beginning. So it'll be very cool to see cuHARM develop over the next couple of years.
Yes, that would be nice. But soonish there should be something coming out. So
nice.
Yeah.
Very good. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.